here to this file. So both of these files, by the way, you do have access to. So if you go to the Blackboard site, so this is the Blackboard site for our class. If you go to Labs, about 30-ish minutes ago, I put this up on the site. So we have this lab here available, and so both of the files that we're going to be looking at today are there for you to download. And by the way, when it's time to turn this in, it's going to be like any other online lab. You're just going to click on the name here, and you're going to submit your report, which doesn't necessarily have to be this report here, but it could be. It probably would be easier for it to be just this same file, but it doesn't necessarily have to be. As long as the information is there, the actual, what the rest of the file is doesn't matter. So if we had been in lab, I would be talking to you about density and about how density is not the same as weight, and so I guess since I'm trying to make this as similar as possible to if we had been in lab, I'll go ahead and talk about that here as well. I talk about this in the lecture videos too, so this is going to be a bit of a reiteration, but that's okay. So density is very, very often confused with weight. People think of things that are dense as being heavy, and while that is very often true, it doesn't have to be true. So if you have something that is very dense, but you only have a tiny little bit of it, that's not going to be very heavy. It's going to be relatively light, unless it's like, neutron star material, in which case you're dead, because it would crush you with its gravitational well. But anything other than that, if you only have a little tiny bit of it, even the most dense stuff on Earth, if you just have like a marble-sized bit of it, it doesn't weigh all that much. It could weigh a lot more than it seems like it should, but it doesn't really weigh all that much. Whereas if you have something that is low density, like styrofoam, if you get a piece of styrofoam the size of your bedroom, that's going to weigh a bunch. That's going to weigh enough you're not going to be able to lift it, even though it is very, very low density, especially compared to the really high density stuff. So density is not just weight. It is weight or mass, how much stuff you have, per volume. So how much stuff you have and how much space over which it is spread. That is density. So in the lab, what we were going to do is we were going to have what's called an inquiry experiment. And essentially I was going to just tell you, here's what I want you to find, and here are the tools that you have, go for it. So inquiry experiments are essentially designed to give you as little information as possible, and then you work out the rest. And telling you what you have available and what you're expected to find is pretty much the least amount of information you can get. Now things are going to be a bit different for us here today, just because, again, I don't have, we're not in the lab. I can't actually have you measuring stuff. So it's going to be a bit different, unfortunately, but we're going to make do. But we're still going to try and at least do some of the same things that we would have done in lab, just not with our own hands. So the first thing that you would find is the density of water. You would confirm, as it says here, the density of water. We say confirm because I do actually expect you to know what the density of water is. Partially because it's a really important thing to know, and partially because it's super easy to remember. It is just 1. It's 1 gram per mil. That is the density of water. And so we're going to confirm that in the lab today in 3 different trials. We are also going to find the density of an unknown liquid. So this will have a density that is not 1 gram per mil. And we're going to again have 3 trials here. We're going to, well, we would have found the density of a regular solid. I couldn't really figure out a good way to do that just really quickly here. So instead we're just going to read some rulers. That was going to be the main thrust of this part anyway, because measuring the mass is super easy. You just put it on a balance and read it. The main thing that students are doing in this section is working with rulers. And so you're going to be reading some different distances off of rulers in part C. In part D, going to measure the density of an irregular solid. So we're going to do that using water and a graduated cylinder. And once again, we can't do that the same way we would have done it in a lab. We're actually just going to be reading things off of a file, reading images essentially. And then the last part here with the overflow cans, I couldn't come up with some way for us to even do it just here, because overflow cans are obscure enough things, and what I was going to have you doing with them is not something that I could just Google a picture and find an example of it. So we're just going to talk about it instead. And then finally, actually the very last thing here is just there are some questions at the end. And these you should be able to answer. There's nothing you really need from me to answer these questions. I expect you to be able to answer each of these, and I do expect you to have those filled out when you turn in the lab online. So let's, before we jump into talking about each of these parts specifically, are there any questions about that overview? I guess not. If you're in the process of typing something into the chat, go ahead and keep doing it, and I'll come back to it in just a minute. So let's talk about each of these individual parts here. So, part A, where we're looking at water. Again, in lab, I would have actually had you get a 50 ml graduated cylinder, weigh the graduated cylinder, put some water into the graduated cylinder, weigh the cylinder with water, and then read the volume off of the cylinder to be able to get a mass and volume for the water. Instead, we have pictures. Not ideal by any means, but this is what we have to work with, unfortunately. So what you're going to do is you're going to take the masses that I provide for you and the images of cylinders that I have provided for you, and you're going to work out the density of water for each of these three things here. So this particular sample, there's the water. Remember that you want to measure the volume from the bottom of the meniscus. So you're going to read the volume here. I just give you the mass. Same thing with this one. Read the volume. I give you the mass. And then there's one more here. So again, this is water here. This is not quite the same. I think the rest of these are all, well, I think that one is actually a picture, but the rest of them are just illustrations that someone has drawn. So again, read the volume. There's the mass. So you're going to use those volumes and masses to find the density of water and also do the average for those three and then the percent range, just like it asks you to here. So the percent range is shown right here. It's on that first page of the lab. So it's just the highest minus the lowest divided by the average times 100. So if you get one density that is 0.97 and another density that is 1.01, and then your third density is 0.99 something, the 0.97 would be your lowest, 1.01 would be your highest, and then you would divide the difference between those two by the average. That would be your percent range. One other quick note of caution here. Remember that when you are making measurements and you are reading the measurement, so it's not just being given to you by a screen like this mass is. That value is just given to you. If you are reading a value, like you are here with the graduated cylinder, you always estimate 1 digit past the markings. So if, for example, and this is not what this actually is, but I'm just using this as an example. Let's say, for example, that this meniscus was directly on top of that 5 mil line. So that would be directly on the 85 mils. There are markings here for each milliliter. So if you thought, and again, don't actually do this because it's not 85, obviously, but just for the sake of argument, if it was exactly on the 85, you should not give your value for the volume as 85 mils. Because you can see that it is exactly on the 85 line, you should be estimating 1 digit past the markings, 1 digit past the milliliters, and so it would be 85.0 mils. Or if maybe you thought it was just a little bit past 85, a little bit on top of the 85 mark, maybe it would be 85.2. And that is completely up to you. It is your estimation. And I'm expecting you to do that on all of these. Some of them are different than others. So this one, for example, the markings are milliliters. But down here, for example, these markings are tenths of milliliters. So you would estimate to the hundredths place in this case, not to the tenths place. So for all of these things, except for the ones that are just directly given to you, like these here. So like this one just tells you, it goes from 50 to 60.5. Like it's just given to you. There's no measuring there. Same thing here, it's just given to you. So if it's something that you are reading with your eyes and measuring with your eyes, then I'm expecting you to estimate 1 digit past the markings. Okay. For part 2, it is essentially the exact same thing, just with something that's not water. And so here we have, again, a volume for you to measure, and I give you a mass, a different volume for you to measure, and I give you a mass, and then a third volume, and I give you a mass. And this is the same liquid for all three. So again, I am expecting you, in part B, to get the average of those three and get the percent range for those three. And I know what the density is because I made up the numbers. And that's how I'm going to be grading you on this stuff, is that you do the calculations correctly and you make the measurements correctly so that you get the correct densities or distances, as we'll see in a second. Now, if you're worried because I just told you, it's your estimation, what if I estimate differently than you? Unless you are way off, I'm not going to take any points off. So like if I think something is 7.2 mils and you just saw it differently and you thought it was 7.1 or 7.4 or something like that, I'm not going to count off for that. Now if you say it's 8, then I'll be like, oh, okay, well that's not the same. That's very different. But if it's something where I can look at it and see like, yeah, I can see where they saw that. I can see where they got that from. I'm not going to take anything off of that because again, it is just it's a personal estimation. It's just what you think it looks like it's closer to. So if our two estimations are off by 1/10, that's perfectly fine. That's expected. If our estimations are like 20% different or 50% different, so like, you're off by like a whole mil from what I have, I'm like, okay, that's not an estimation at that point. You just read it wrong. Like if you clearly just read it wrong, then you would get counted off. Okay. And by the way, really the only way that you can get way off on these is if you, again, mistake what the individual little marks are. So like again here, each of those little marks is 1 mil. Over here, each of them is 1 mil. Over here, each of those is 1 mil. And then here, each of those marks is a tenth. So you have to pay attention to what the big numbers are and how many divisions there are between them. And so that will help you figure out what digit you're trying to estimate. Okay, so that is part 2. Part 3, or C, I guess, was going to be a regular solid. So I had some just like rectangular shapes and some cubes that I was going to have you measuring the density of. Can't really have you doing that here. So instead, I just have some rulers for you to read. So there are 4 different things that are measured here, different rulers, and I want you to read those lengths and just tell me what they are. That's it. Now again, I do expect you, number 1, to actually be close and to have to be estimating the last digit. So just as an example here for the first one, and I won't do this for all of them, but just for this first one here, we have centimeters marked, and by the way, this one isn't marked, but it's also centimeters. The one here with the pencil, that's also centimeters. So we have, this is 2 centimeters, and it's a little past the 3 mark there. So you would not report this as 2.3 centimeters because the tenths are measured. There are markings for the tenths. And so this next digit here, that's what you would estimate. Now, I'm not going to tell you what I think it is. You should make your own estimation. If your estimation is way different than mine, then I might say, okay, one of us needs glasses. But I would bet that your estimation won't be all that much different than mine. But it is very clearly somewhere between the 1, 2, 3, and 4 mark. So it's somewhere between 2.3 and 2.4, that are red line there. And so I will let you estimate how far in between it is. Is it closer to the 3? Is it closer to the 4? Is it about halfway? It's up to you. So it'll be the same thing for the other ones. Part 4 is a little bit different. So this is, actually it's not really good over here. So part 4, or part D, is an irregular solid. So irregular solids, you can't measure their density using a ruler, just because you can't measure the size using the ruler because it is irregular. Well, I guess technically I really shouldn't say that. If you had a lot of patience and a lot of time, and you were very precise, you might be able to measure the volume of an irregular solid using a ruler. But as the lady from the meme said a long time ago, ain't nobody got time for that. So, instead, what we usually do with irregular solids is we drop them into some water. So if you take some water and you know the volume of that water, and you take a solid, you get the weight of that solid, and then you drop that solid into the cylinder. Archimedes' principle says that the solid is going to displace the exact amount of water that is equal to its own volume. So if you have a 20 milliliter volume piece of something, when you drop that into water, it is going to displace 20 mils of water. And so what you're going to do with these two is pretty straightforward. You're going to take a look at the before and after to find the volume of the solid, I give you the mass, because again, there's no way to know the mass unless I give it to you in this situation, and you will find the densities. By the way, this says that this is jade. Do not just go onto Google and find the density of jade. I very specifically made my mass here so that it would not match what Google says is the density of jade. So if you do this and you go check your answer and it's not exactly what Google says, that's a good thing. I didn't change it like drastically. No, Google didn't say that the mass of jade or the density of jade was 10 and I made it to be 2 or anything like that. It's still fairly close, but I did specifically make it different so that you couldn't just Google it. Not that it's all that hard to do. Honestly, finding the density is probably just as hard as Googling it, because all of this stuff is just right there. Let's see, there's that. Yes. So all the stuff that we're looking at right now is what you'll use to do the lab, and they are all available right here. So if you go to the Blackboard site, you go to Labs, just scroll down to the bottom, they're right there. So there's the document for the lab itself, and then there's the quote data. It's not actually data, really, but what we're going to be working with for data. And that is it for those 4 parts. Any questions about those? Any questions? I guess my video's still not working. Oh well. 1 decimal passed on centimeters. If the, let me see. So yes, this one is a bit more troublesome because it doesn't have all of the tenths marked, but it does have the halfway marked. So I've seen different rules for how to handle this, where you don't have tenths marked, you just have something in between. So there are markings, but they're not regular essentially. They're not at least a decimal regular value. For this one, let's just do tenths of a centimeter, because I believe when I did mine, yeah, we're just going to do just tenths of a centimeter. So because they have centimeters marked and they have a half centimeter marked, but with only half centimeters and such a small space there, I don't think it's reasonable to say you could estimate to the hundredths of a centimeter with those markings. So we're just going to do tenths of centimeters on that one. But all the rest of these are, you have tenths of centimeters marked, and so you would estimate to the hundredths of a centimeter. So it would be something, point something something. You would have 1 digit before, at least 1 digit before the decimal, and then 2 after the decimal, the tenths and the hundredths. Since each of those have a tenth of a centimeter marked. Sig figs on density, yes, I do expect you to follow sig fig rules on the density. I think everything I gave you has 3 sig figs. All the masses, well, some of them have 4. So you should end up with either 3 or 4. Because I don't think any of the volumes will end up with 2. I don't think. all the volumes should end up with 3 at least sig figs. So you should have either 3 or 4 sig figs in your densities when you finish. So just follow the normal rules for sig figs. So if your mass and your volume both have 3, well, if either of them have 3 sig figs, and that's the smaller, then your answer can only have 3. If both of them have 4, then you can have 4, and you should have 4 in your answer. Ellie, I am recording this right now, and what I'll do is I will upload this to YouTube, to the same place that we watch the lecture videos, and you'll be able to watch the first 20 minutes after we're done here, just on your own time, but hopefully soon, because it shouldn't take you too long to finish the lab. So if you just, as soon as we're done here, go and watch that, work on the lab, you should be done by the time we would normally be done in lab. That is the idea. Okay. It might take a few minutes for the video to show up, just because I have to sign into that account, and I have to put it in to load, and it has to upload to the site, and then YouTube has to process it. So it'll be a few minutes. It won't be immediately as soon as we're done that it becomes available, but it shouldn't be more than 10 minutes or so. Any other questions about parts A through D? That's a good question. There's not a due date on the assignment in Blackboard right now. I'd like you to get it done today, just because we would have done it in lab. I don't want you to put it off, because then it just won't get done. So I think what I'll do is when we're done here, I'll go into Blackboard and I'll set the due date for let's say maybe tomorrow at 5, just in case something happens, and something happens tonight and you need to email me and I don't get back to you right away. I should be able to get back to you before 5 tomorrow. Actually, I know I'll be able to get back to you before 5 tomorrow. So I'll give you a little bit of time if I don't get back to you right away. So we'll say 5 tomorrow. We'll have it be due. But if you can, get it turned in today, just to be done with it. Any other questions? Okay, if there are no other questions, I want to just real briefly here talk about Part E. So this is something that we would have done in the lab if we were all there. And I think it's actually pretty fun. I think that the overflow can is pretty cool. And so I want to, at the very least, talk to you about it. Obviously, we can't actually do anything with it since we don't have an overflow can here. Try to explain what we would have done so you can maybe help yourself expand your mind a little bit and how you think about things, because the way this was going to work is, let me see, can I write on this? It's not going to let me write on, is it? Okay, let me pull something else up to write on. What? Can't find the file for the blank presentation? That's different. Okay. disabled. You are going to answer the questions at the end of the document titled density, and you're going to essentially do those same things that are described in the document density, but you're going to do them in the way that I talked about it here. So since we can't actually do the measurements ourselves, you're going to be looking at the images that I provided and the data that I provided to get the same data. So you're going to be doing most of the same stuff, just using what I provided instead of doing it hands-on in the lab. And then you're going to answer the questions at the end. So there's, I think, 4 questions at the end of the lab. So if you want to turn in that file, data for density, what's it called? Density inquiry, yeah. So if you want to turn in this file as your lab, and so, just come in here and it should let you type stuff in there. I don't know. Oh, there it is. It's going to let you type something there, I guess. Well, maybe not. So if you want to try to go in there and type your answers into those blank pages, or put in new blank pages if those blank pages are giving you trouble, excuse me, then you can feel free to do that. If you want to do it on a separate page, that's fine too. Just as long as I have all the stuff that I asked for. So the density of water, all 3 of them, and then the average and the percent range. Same thing for the unknown liquid, the 3 individual densities, the average and the percent range. The measurements of the stuff with the ruler, and then the 2 densities for the irregular solids. And then the questions at the end here. So as long as you have those answered, that's all I'm looking for. So if you want to write that out on a piece of paper and just take a picture of it and turn that in, that's fine too, just as long as I have all the answers. Okay, let's see here. Is it going to let me insert a blank slide? There we go. Okay. So, for that part E, which we would have done in lab, what we would have used is what's called an overflow can. And what an overflow can does is it is essentially this metal cup, and so it goes all the way around up here, and it's round on the bottom as well. But there is a little opening, I guess you can say, on the side, very much towards the top of the overflow can. And so what you do is you can take this and you can fill it completely with water to the point where it is over that outlet, and the water will drain out of it until it reaches the bottom of that outlet. And obviously, because water has high surface tension, it does kind of stick there together. It's not fully below the outlet, but it does stop flowing out at some point. And so then what you do with the overflow can is you can take irregular sized objects, like a beaker, for example. So we take a beaker here, with its little markings on it, and we take that and we put it into the overflow can so that it sits in there. Oops. Goodness, I don't know what's going on with my pen here. It's not liking me going back like that. So it sits in there, and when you dunk that in, you have to kind of scoop the water with the beaker because there's air inside the beaker, and that's not what we're trying to measure the density of. We want the density of the glass itself. And so we kind of scoop the beaker in there at an angle so that it scoops up the water as we're putting it in, so that it doesn't displace any extra water, essentially. We only want the glass to be displacing water, not the air inside of the beaker. And so when that happens, more of the water comes out. Again, because of Archimedes' principle. Because you put something extra in there, it takes up volume, and so it pushes a little bit of that water out of the overflow can, and you can catch that, usually in a graduated cylinder, and measure the volume of the water that comes out. So this is a very, very common way of measuring the volume of something that is irregular in shape, which a beaker is. Beakers kind of look like they're regular in shape, but they're actually not. They're actually quite irregular, especially because they're just very poorly made. They are just sciencey cups. That's all beakers are. And so they, like the base of the beaker is not the same thickness as the walls, which is not the same thickness as the brim. It's all different. So you can do that with the 50 ml beaker as well as the 100 ml beaker, which is a bit bigger. Apologies for my terrible drawing skills here. So the 50 and the 100 ml beakers are small enough that you can fit them into the overflow can at an angle so that you can essentially scoop up the water as you're putting them in there. The 250 ml beaker, on the other hand, is too big. And that's actually not to scale. It's actually quite a bit bigger than the 100 ml. It's so big that if you try to put it in there at an angle, essentially it can't fit. Like, it's the same width as the overflow can, and so there's no way to get it into the overflow can at an angle to scoop up the water as you're putting it in. And so what I was going to have you do in the lab was work out some way of getting that 250 ml beaker into the overflow can and measuring its density using the overflow can, even though you can't actually put the 250 ml beaker in there without either pushing out extra water or having some other trouble. Because if you just take the 250 ml and just push it straight in, just straight down, it displaces extra water, and so you're not actually getting the volume of the beaker, you're getting the volume of the beaker and the gas that was inside the beaker at the beginning, which is not what we want. We want the volume of just the beaker. So with all that being said, and don't feel bad if you can't think of anything, because it's very difficult to do this without having your hands on the material. I mean, it's not even really easy if you have your hands on the material, but does anyone have an idea of how we could measure the volume of a beaker that is too big to fit in the overflow can at an angle? How could we get that in there and still measure the volume of just the beaker? Any ideas? Let's see. That's a good idea. The big problem with that is that there is no direct proportionality. So we could not take, for example, 5 50 ml beakers and get the same as a 250 ml beaker for a couple different reasons. Partially because, like I said, there's just no direct proportionality. A 50 ml beaker is not 1/5 the size of a 250, and also because, again, they're just terribly made. They're just cups. They're not made with precision, and so you could take one 50 ml and take another 50 ml and they won't be the same size. So it's a good idea, but just because of the way that things are made, it's not going to work for us. What other ideas might someone have? So that is another thing that is very often suggested, is what if we take the water, what if we put water in the 250 ml beaker? And I'll tell you right now, there is a way that that could work, Daniel, but only one specific way. So let me ask you a question, and maybe this will lead you in the right direction to understanding the proper way to do it. What water are you going to put in the 250 ml beaker? Because it could possibly work, but you can't just put any water in there. By the overpour, do you mean like the stuff that comes out as you're pushing the beaker in? That would work. Yes, that would work. So for those of you that maybe can't see the chat or are not looking at the chat, so what Daniel suggested was that you take the beaker and you just go ahead and just push it in. Now, if you remember earlier, I said that if you just push it in there, you're going to push out too much. Too much water is going to come out. But if you go ahead and do that, and you catch the water as it comes out, so you just go ahead and just say, I don't care that I'm putting out too much, I'm just going to push it in there so that the 250 is now inside there, but now the water level is down here. It's way lower than it should be, because you should end with the water level still at the spigot. That should always be the ending point. It should always be the starting point as well. And so what Daniel suggested is when you push that in there, catch that water in something else. So catch all that extra stuff that comes out, and once you get the beaker in there all the way, take that water, put it back. Now, one thing that you have to be careful of here is when you pour that water back in, you better have something ready to catch the water that's going to come out again, because all the water that you pushed out, you're putting back in, but now there's a beaker in there, and so you're going to have some of that water come out again, and the water that comes out will be exactly the same as the volume of the 250 beaker. So yes, Daniel, that would work, but only if you use the water that was already in the overflow can to begin with. I've had a few students that have tried putting water in the beaker to start with, so they have the can full, and then they have the beaker also full, and that will not work because now you just have tons of extra water. The key to this is really all the water that you have at the beginning. You know exactly where all of it is at every point. You don't lose or add any water to it. So you can maybe push some of it out, but as long as you collect it and you know where it is, that's perfectly fine. Just so you all are aware that the couple other variations, because there are about 3 different ways that you can do this that all work on the same basic principle. You could also take the overflow can and take all the water in it and just dump all of the water into something else. So, once you have it full and it stops dripping, take all the water that's in there, dump that into a different container, put your beaker in, and then dump all the water back. That would also work, because again, all the water that you have the exact amount of water that you need to make it exactly full. Just put that water somewhere else, put the beaker in, and then pour that water back in. And so any water that comes out at that point is only from the beaker being present. Let's see, what was the third way? Now I'm having trouble thinking of the third way. Well, it's not super important. There's a third way that's kind of just a variation on those two. There's really just kind of one basic way. It's just keep track of all the water at all times. It just kind of depends on, do you put it all out? Do you only push some of it out? So it's all kind of variations on the same idea. But that is a way that you can do that if the beaker can't fit in there all on its own or at an angle. And so I'm a bit sad that you all were not able to try and work that out on your own in the lab. It's always kind of fun to have students trying to work that out and then asking for help and me giving them clues to think about how to possibly do it. It's pretty fun, at least I think it's fun. So it's kind of disappointing you all didn't get to do that, but at least we got to talk about it. Maybe expand your mind a little bit to think about different ways of doing things. I think the main issue that students come up against in this last part is that they get so fixated on the fact that they were able to get it to work with the first two size beakers and the overflow can and nothing else. And so they get kind of fixated in thinking, well, I need to be able to do it with just this stuff. Whereas, we are scientists. We are not limited in terms of our glassware, for sure. Sometimes it's helpful to think, well, what if I used some other tool? What if I used other things to help me, like another container to dump the water into? So thinking kind of outside the box. Thinking about, I might have only been told that I'm using these things, but what if I used an extra thing? Will that work? Hey, it does work. So it's kind of fun to work those things out. Okay, I think that is everything that I wanted to talk about. So yeah, there's the density assignment there. Yeah, I don't think there's anything else I wanted to talk about. Are there any questions? Before I let you go? I guess I also wanted to ask, did everyone see my email about the exam? Okay. I assumed that everyone did. It's also an announcement on the Blackboard site, so you can catch it there if you didn't happen to see that come through. So you can check that out. You didn't see the email about us meeting here today? That's strange. I sent it out to the whole class, but I said specifically in the email that it was for Group B. So Bailey, if you missed stuff at the beginning and you didn't hear, I am going to be uploading the whole video of us talking to the YouTube site here in just a couple minutes. So you can catch it there if you missed some stuff. I don't know why that wouldn't have gone through to you, but yeah, you should have gotten an email. I think that was around 10:30 this morning, something like that. I sent out an email. So I believe sometime tomorrow I will be putting up a video review for the exam. And that would just go up onto the YouTube site as well. I might have a review from a previous semester that I can just put up there so I don't have to make it all over again. If I can find one of those, I'll just put it up there because my review doesn't really change from one semester to the next. But if I can't find one, then I'll just make a new one. It takes about an hour, but I can that. So be watching for that tomorrow. Um, I should be getting a lot of stuff done tomorrow.